theorem, if f of x equals the sum from n equals 0 to infinity, c sub n x minus a to the n. So in other words, if f of x is represented using a power series, and it has radius of convergence r greater than 0, so that means that it's convergent on some interval. By the way, the generic way of creating that interval is taking the center of that interval, and to get the left-hand endpoint, you subtract r, a minus r. To get the right-hand endpoint, you add r to a plus r. Then on the interval, a minus, so in very complicated language, I'm saying this is I, the interval of convergence. Then on that interval, it turns out that f, the power series representation of f, is not only continuous, it is differentiable and integrable. That's what number 1 and 2 say. And we integrate it and differentiate it in exactly the way you would want, term by term. So let's think about that. When I say a term of a power series, a term, any one term is given by this formula. The first term you'd get by plugging in 0, since the starting value of n is 0. The first term you would get is by plugging in 0 wherever you see an n. The second term you'd get by plugging in 1, and then so on and so forth. So you can use that formula to represent any term. How do you take the derivative with respect to x? So c sub n is a constant with respect to x. How do you take the derivative of c sub n times x minus a to the n power? What rule do you use? Don't even need the chain rule, because the inner function's x minus a. The derivative of x minus a with respect to x is 1. So it's just the power rule. So just for that term, I'm not writing down the answer yet, but just for this term, the derivative is, well, you bring the n down, n times c sub n, or c sub n times n, either one. X minus a to the what power? N minus 1. Isn't that a generic formula for the derivative? But wait a minute, that works for every term, so we need that summation notation in front. So this is a way to say in one neat and tidy formula. Oh, by the way, though, we're going to start at 1 when we take the derivative. And I'll tell you why in a second, but bear with me for a second. So this is a neat and tidy way to say, to take the derivative of a power series, we do it term by term. Now, it might be easier to see if you multiply it out, or if you write it out longhand, I mean. So if you write out a power series longhand, what does this fancy notation really mean? Well, what's the first term? Plug in 0, what do you get? C subscript, plug in 0, you get C subscript 0. X minus a to the 0 power?
1. Right?
1, so it's just the first term is C sub 0. Plus, what's the next term? Plug in 1, what do you get?
C1 plus x times x minus a.
X minus a to the 1. Plus C2, now you're getting the pattern. You're going to use your superpower of pattern recognition. You don't even need the formula anymore. C2, well, maybe you need it for this one. X minus a to the second power, because you're plugging in 2. Remember, you started at 0, so on the third term, you're plugging in 2. So now what are you plugging in for n?
C3, x minus a, 3.
Now you don't need to look at the formula anymore. Use your superpower of pattern recognition, and then on and on and on, right? Plus dot, dot, dot. And so what we're saying is, if you take the derivative of this guy, term by term, this is saying you can take the derivative term by term. This guy, the derivative of this guy goes to 0, right? So I'm writing the derivatives up here. 0. So that's why we don't start at 0. And then the derivative of this guy is just C1, right? The derivative of this guy is 2C2 times x minus a. The derivative, so I'll write these down. So the derivatives. And then 2C2, bring down, just using the power rule, bring down the 2. Here I brought it in front. Here I put it there. I don't know why. 2C2 x minus a to the 1 power. And then what's the next one?
3C2
x minus a squared, and then on and on and on. So longhand, that's what we're saying, and you're more used to writing out longhand, but that's a real drag trying to do that every time instead of using the interval or the summation notation. Does everybody see why we start at 1 instead of 0 now? Yeah, writing out longhand, that's how you can see that, oh, that when you take the derivative, that first term goes to 0. That term that you get when you plug in 0 goes to 0, so you're going to start the derivative at 1. That's just something you have to kind of remember. But you don't have to worry about that when you write down the integral. So now imagine integrating term by term. So this guy, remember, Cn x minus a to the n represents a generic term. If you integrate that, let's forget about the summation notation. If you integrate Cn times x minus a to the n, what rule do you use? Not the power rule for derivatives, but the power rule for integration or integrals. So, so generically, one term, what do you get? Cn x minus a, what's the new exponent? It's n, but you integrate using the power rule, it becomes n plus 1. Oh, and then what do you have to divide by? The new exponent. So all you did there was state the power rule for integration. Oh, but then we're doing it for all the terms. Better put a sum, n equals 0 to infinity. The first term won't go away for this one, so you keep the 0. And then I suppose you could add in a constant term as well. So plus some constant c. Okay, so that's why we like power series. There are functions we have no idea how to integrate unless we write them as power series. Differentiation's easier on most functions, but still sometimes representing it as a power series and then differentiating, sometimes that's a lot easier as well. Okay, so just remember, term by term. You integrate and differentiate term by term.